For this lesson, we're going to start getting into combustion of all of your natural gas type furnaces. So with natural gas, we got to understand what natural gas combustion is. Well, combustion is a chemical process of rapid oxidation in which fuel and oxygen will produce heat and light. Okay, combustion fuels most commonly used in all of our heating appliances are going to be natural gas, LP, and oil. The three basic elements necessary for combustion to occur in all three of those commonly found type fuels is going to be your fuel, your heat, and your oxygen, which is better known as your combustion triangle. If I have all three of those elements, I can produce fire. If I remove one of those or alter one of those, I'm either going to have complete combustion or incomplete combustion. So, heat is required to initiate the reaction as the fuel and oxygen combine. And heat and light energy is then released once I have ignition. The following chemical formula shows the products of stoichiometric combustion. So what this formula is talking about is if I have methane and I add some oxygen to it for my combustion, I am now going to create carbon dioxide, water, and energy. What that formula is basically saying is I have a combustion reaction. I have methane and I'm adding oxygen to it. I am now going to create carbon dioxide and water. When I think about that wonderful term, stoichiometric combustion, all I am basically saying, and I'm sounding really, really intelligent, is all I'm talking about is perfect combustion. So go ahead. You can talk to somebody and say, do you know anything about stoichiometric combustion? I tell you right now, they'll look at you like you have three heads. But really all you are saying and mentioning is perfect combustion. In perfect combustion, I'm going to be able to have carbon dioxide, water vapor, and energy as my byproduct of combustion. When this combustion, the burning of fuel occurs with the exact amount of oxygen needed to change that carbon and hydrogen molecules into water and carbon dioxide. With perfect combustion, it is very, very difficult to achieve in the real world. Perfect combustion can be achieved in laboratories when you're able to control the amount of oxygen and the elements and everything. But when we are out in the real world and we're working on equipment, we're not really going to see perfect combustion. Which means by perfect, we're burning every last element of that carbon and hydrogen and atoms to create that water and carbon dioxide. All we can do as a mechanic is get it as close to that perfect combustion as we possibly can. And we call that practical combustion. It's practical. More real to life. Okay, gas furnaces can almost never, ever achieve perfect combustion, okay? But they can achieve complete combustion or practical combustion. Okay, complete combustion is going to occur when fuel is burning in the presence of excess oxygen to produce water and carbon dioxide. But however, we must understand the perfect combustion formula in order to analyze the combustion process. In the perfect combustion formula, that ratio of oxygen to fuel is 2 to 1. In that, the only products of combustion are carbon dioxide, water, and energy. Well, in heat, the concentration of heat is needed to even start that chemical process of combustion. We got to have some sort of ignition source so that we can actually ignite what we're trying to burn. The heat required to initiate combustion is called the ignition temperature. The ignition temperature is usually provided by either, again, a pilot or a hot surface igniter. Okay? The ignition temperature of natural gas is anywhere between 1100 and 1200 degrees. The ignition temperature of LP gas is anywhere between 920 and 1020 degrees. Once combustion has begun, the chemical energy in that fuel is released and converted to your heat and light energy. So in other words, when I light natural gas, I can actually see it burn. And I can feel the heat coming off of it. As long as the fuel and oxygen are present at that correct ratio, no additional external input of heat is needed to sustain combustion. So again, back to that combustion triangle. All three of those elements have to be correct in order for us to achieve complete combustion. I have to have the correct amount of gas. I have to have the correct amount of air, and I have to have the correct temperature in order to ignite my fuel gas. Combustion can only occur when that ratio of air to fuel is within those acceptable ranges. The ideal ratio of oxygen to methane is 2 to 1. The ratio of air to fuel must be as much higher, probably about around 10 to 1 for methane. The higher the ratio is because air is made up of 78% nitrogen and 21% oxygen. That's the reason why we got to have that different ratio of air between what we're burning. In a mixture of fuel and air, the fuel's flammability limits are defined as the range of fuel concentrations within which the fuel will burn when an ignition source is present. So here we go. We got methane here. The upper flammability limit for methane is about 14%. The lower flammability limit for methane is about 5.3. Okay? So this here kind of gives you a unique look at, again, the gas properties of your different gases, the difference between your lighter gases and your heavier gases. If you notice by propane there, it has an upper flammability of only 9.5%. So it's a heavier gas, so it's going to have a quicker light off because it's heavier. It's got more substance to it versus your methane, natural gases, and stuff like that. So if we look, we will see that in order for combustion to occur with natural gas, your fuel and air mixture must have a concentration of anywhere between 4 and 14%. The ideal concentration of natural gas is between 8 and 10%. A concentration of less than 4%, their gas is going to burn too lean, which means there's not enough fuel for combustion. A concentration of more than 14% creates a mixture that is too rich, which means there is not enough oxygen available for all the fuel to burn and all the fuel that is actually being present. The amount of air required for combustion is different for each fuel source. You'll have your primary air. Your primary air is the mixture, is the air that is mixed with the fuel prior to ignition. There must be enough primary air available to support ignition. So as the oxygen is consumed during your combustion process, it has to be replaced. In order for us to replace what is being burnt, we have what is called secondary air. And that is the air that is added to the flame after ignition to help support combustion. Secondary air surrounds the outermost area of the flame and maintains the combustion process. Your primary and secondary air are commonly referred to as combustion air, which is the air needed to complete combustion. So here we are. We have a nice little diagram here. Here is my gas coming in. Here's my gas orifice. Here's my gas coming out, which is being ignited. My primary air gets sucked in through my tubes and mixes with the gas that's coming out of my orifice. And that is what helps ignite the gas. Once my ignition occurs, I have my gas and air mixture, which is coming out of my burners all the way through. As I have my ignition, my secondary air, which is what surrounds and what's surrounding the air, helps support that combustion and helps burn off all of my gas so that I can have complete combustion. All fuels contain hydrogen and carbon atoms in different amounts. Your substances that contain only hydrogen and carbon are referred to as hydrocarbons. So since hydrogen burns more quickly and at a lower temperature than carbon, hydrogen burns first, using the oxygen from the air that is needed for complete combustion. Hydrogen flames will have a bluish color to them. Since the hydrogen in the fuel burns before the carbon, carbon atoms must travel to the outside edge of the flame to get oxygen from the secondary air for complete combustion to occur. Carbon atoms burn more slowly and at a higher temperature than hydrogen. Your carbon flame produces a bright yellow flame. Your flame color indicates when proper amount of primary air is present in a gas furnace. When you are looking at a natural gas furnace, the flame should have a blue inner core surrounded by a light blue. This indicates that there is no unburned carbon. When you look at those furnaces, that's what you want to see when it lights off. It should be a nice blue color. Incomplete combustion occurs when a flame does not receive enough oxygen to finish the combustion process. If there is not enough primary air, the flame will have yellow tips. If the yellow tips are due to carbon particles that are not being burned. If the outer edge of the flame burns orange, it is due to burning of dust particles drawn in from the primary air and does not have some sort of sign or any issue of combustion process. Sometimes that's actually pretty normal in natural gas furnaces. You'll see the flame have a nice dark, nice light blue, but every once in a while you'll see maybe an orange little flicker going on inside there. Nothing wrong with that. If you see yellow, yeah, you might not have enough primary air. You're going to have to adjust. Okay, so here you can kind of see, if you look at number 1, this is a really crappy looking flame. Look how yellow this is. This is incomplete combustion. Probably very little air going into that burner. As we introduce more air to it, you can see that the flame becomes a little bit more steadier. We start to have a little bit of blue, but we still have a lot of orange and yellow going on in here. If we add more air to it, it becomes a lot more blue. And then we have enough air-fuel ratio going on, and we have a nice blue flame. This is what we want to see, is number 4. Okay, carbon monoxide is a byproduct of incomplete combustion and is a colorless, odorless, and highly toxic gas that can be fatal in a lot of buildings. All service calls should include inspection of the flame during operation to check for incomplete combustion. All of your heat exchangers should be inspected for cracks as well. A carbon monoxide level should be checked with a carbon monoxide meter. Too much carbon monoxide in the blood can cause the person to die from lack of oxygen. Before dying, the person will feel tired and may fall asleep without knowing they are being suffocated due to the lack of oxygen. Carbon monoxide has also been associated with Alzheimer's and attention deficit disorder. There are two types of fuel primarily used in your natural gas furnaces, obviously natural gas and your propane, liquefied petroleum. Natural gas is obtained from gas deposits in the ground. It is lighter than air and consists of about 95% methane and 5% ethane and other hydrocarbons. It has a heating value of about 1,000 BTUs per cubic foot and about 1,100 BTUs per cubic foot. Okay, to burn 1 cubic foot of natural gas, 10 cubic feet of air is going to be needed. However, some excess air is needed to prevent any incomplete combustion from occurring. Therefore, about 15 cubic feet of air is used for each cubic foot of natural gas, which provides about 50% excess air. Excess air is any secondary air that exceeds the amount of air necessary for complete combustion. So in many ways, you could kind of think of excess air as air that's actually left over. By designing furnaces to take a certain amount of excess air, manufacturers provide a safety buffer in case of damage or malfunction that impedes airflow and reduces the amount of air needed for combustion. Furnaces with lower efficiency ratings take anywhere between 20 and 50% excess air to ensure complete combustion. Your higher efficiency furnaces use as little as 10% excess air. Excess air is important for condensing furnaces as it reduces the dew point of your flue gases. Dew point is the temperature at which a gas condenses into a liquid. By reducing the dew point, excess air causes the flue gases to condense at a lower temperature, ensuring that the furnace will capture the heat of condensation from those flue gases. As a mixture of 1 cubic feet of natural gas and 15 cubic feet of air is burned, it yields about 1 cubic feet of carbon dioxide and about 2 cubic feet of water vapor. It also yields 12 cubic feet of nitrogen and 1 cubic foot of oxygen, which are left over from the excess air used in the combustion process. If the furnace is not designed to condense the water vapor and the flue gas gets low enough, the water will corrode your flue pipes and cause the products of combustion to leak into the space. Condensation of water begins anywhere between 180 and about 200 degrees. If there is not enough primary air on your burners, the flame will be noisy and jump around above the burner. If the exhaust contains carbon monoxide, there is either too little or too much combustion air. LP gas consists of liquefied propane and butane. It is mostly propane with some butane. LP gas is heavier than air, and it can be easily liquefied under pressure, stored and transported in cylinders and tanks. And when the pressure is reduced as the LP gas leaves the tank, it vaporizes and changes it into a gaseous form where it can be burned. Propane will boil at negative 44 degrees Fahrenheit at atmospheric pressure and has a heating value of 2,500 BTUs per cubic foot. Butane boils at 32 degrees Fahrenheit and has a heating value of 3,200 BTUs per cubic foot. LP gas can produce more heat per pound of natural gas. It requires more oxygen as well for complete combustion. To burn 1 cubic foot of LP gas, you're going to need 24 cubic feet of air. To burn at about 35 cubic feet of air is needed to provide 50% excess air. Okay, propane requires 32.5 cubic feet of air for each cubic foot of gas. Butane would require 45 cubic feet of air for each cubic foot of gas.